This set of lectures is part of the Institute's Golden Jubilee celebrations. So this year is the 50th year of IMSC, and part of these celebrations is we are having various academic events throughout the year. And the Theoretical Computer Science group in particular is organizing this bunch of lectures once a month, a day of lectures at some theme related to theoretical computer science. We have earlier had sessions on randomized algorithms, graph algorithms, and so on. And so today the theme is concurrency, and we gave the title Concurrency in the Multi-Core Era, mainly because rather interestingly, concurrency is perhaps the theme that made big changes in the development of computing. Going away from batch processing to interactive computing was one of the big turning points of the 70s and 80s. Now, it's even difficult to think of something like that being considered revolutionary. But it was a huge development which led to multi-threaded operating systems where concurrently you could be running many different processes, printer could be doing something, main memory could be doing something, many different, so what you call threads today came out of the study of concurrency. And very early on people realized that programming concurrency was hard. And but over a period of time as operating systems stabilized, in some sense, and in parallel there was a lot of work going on in distributed computing, pretty much I would say it's saturated to some extent. But then in the last 10 years or so, there has been a big revival, and now mainly because of this multi-core architectures, people have realized that concurrency is something very basic and we have to look at it very seriously. And the main problem is that hardware is increasingly reaching thermodynamic limits. It's clear that you need to work with many different processors, and at a very low level you need algorithms and code that manipulates multiple cores. Now, if you try to take standard algorithms there and simply try to map it, first idea of course is take whatever sequential algorithms you've got and simply map it onto concurrent architectures. Doesn't work. So you have to rethink. And many of the problems are, on one hand, familiar in the sense you are revisiting territory from the 70s and 80s. Unfamiliar in the sense that it looks very different from C programming and Java code. Right? So there is a lot of very interesting research that's going on, and we think it's interesting and important from the viewpoint of programming languages, from the viewpoint of theoretical computer science, models of computation, from algorithms, automata theory, kind of things that we understand. There are a lot of very interesting ones, and we thought today would be one chance for us to explore some of these issues. So this is by way of introduction. Mr. Ramchandra, my science, he will chair today's conversation.
Okay, so let's see. That doesn't work. Okay, so I'll work like this. So, as Ramajam said, we'll move from the familiar to the unfamiliar. So this is supposed to be familiar, and by the end of the day, we'll reach the unfamiliar. That's the idea. So this is, I'm going to look at things which are you'll find in textbooks, okay, and but we need to actually look at this a little and try to understand. And in particular, the reason for this lecture was I spotted some mistakes in some textbooks, so I thought that I'll at least discuss that. So this is a part of a series of lectures I gave, and so I'm not going to do all the lectures. So this is the textbook which I followed, Greg Andrews' Foundations of Multi-Threaded Parallel and Distributed Programming. It's a very old textbook and very popular. Okay. Here's the big pointer. No, I'm happy with this. No problem. Okay. So I'm going to use Java as my basic programming language because it already allows concurrency, and we'll see what happens in this language. So if you want to define a thread in Java, so this is how you do it. You extend the class window with, you extend the class thread with whatever your class name is, in this case window, right? And in this case an ID is given to that window, okay? And then there is a run method, and what all this run method does is it prints window number so and so, okay? And then you go to sleep for 1000 milliseconds, okay? And there is an interrupt. There's an interrupt routine out here. So the idea is, what this does is each window just starts, prints this window something, okay, and then goes to sleep, right? Okay. So this is the class, and now we create the main program. Okay, so here we have, so we create objects of type window and we start them off, and to do that, this is, so here is a loop. So there I'm using 5 windows out here, okay. So I create a new window object and I call wi.start, and the start method will actually start running the run method inside the Windows class, right? So that's how. Okay. So okay. The run method is so the why I use start rather than run is basically returns to wherever it's called from, okay. Whereas start just calls it, and then after that, when that window, when that class is over, when that method is over, the process dies. That's all that happens. That's the difference between start and run. Okay. So this. Okay. Right. So this is a more complicated example. So this I did. So I have a main program in which I created 5 threads and started them off. Okay. Now if inside these 5 threads I want to create, let's say, 5 more threads, then how should I do it? Okay. So, but so you can't just do the same thing again. So there's a different way in Java to do this, which is you implement an interface class called runnable. Okay. And so the only difference that happens here is you say window implements runnable instead of window extends thread, okay, and then everything else after that is the same. Okay. So the only difference now is that this runnable class allows you to create threads inside threads, which was not possible earlier. Okay. Now here is how you call it. First you have a window class, then which extends runnable, then you have a thread, you create thread objects, and now what you do is you first create window objects, you create thread objects, and then you start the thread. Okay. Right. So in this case you have to call the start method in the thread class, okay, because it's only the thread class which has a start method, and that will actually start off the run method in the window class. Okay. So that you can actually now, I mean, this is a more general mechanism, and now you can keep creating more thread classes and more window classes, and you can keep calling. This works. Okay. Just if you have any questions, ask me right away.
Yeah. We have usually 5 threads. Yeah. Then now in each thread we have 5 more threads.
No, not right now. In this I have just created 5. Yeah. But I'm saying now if I wanted, I could have created inside the window class, I could have had 5 more objects of this kind, which would implement runnable, and that would still work, or 25 more objects, whatever. It doesn't matter. The number does not matter. So there are 2 different classes. Thread creates threads, okay, and runnable creates something which is potentially a thread, and it can create potentially more threads, right? Whereas thread just creates a thread once and for all, and starts off. Okay. So I think this is, yeah. So here is a summary. So Java thread is a lightweight process. It's a concurrent process. It has its own stack and execution context. It has direct access to all variables in its scope. And to program a thread, what you do is you define a new class that either extends thread or it implements runnable, whichever you choose to do. You define a run method in the new class which has the code of the thread. Okay? And you create an instance of the new class with new, and you start the thread using start. Right? This is the general mechanism. Okay. Fine. So what actually happens when? Why do we have to do this? Right? In the machine, where are all these threads and so on? Right? Let's see. So here is your multi-core machine, right? Yes, I don't know, maybe some memory. Here are processors. Okay, maybe there is some bus or something which connects processors to memory, right? So this is the hardware. There can be other devices and various other things inside this. So where are all these threads? When this is compiled finally, ultimately it has to run, right, on the machine. So where do all these threads go? Where do they sit? Where do all these threads sit inside? When you run this, when you have compiled this, all this has become machine language, right? So where is all this machine language code? Where is the thread? What is actually a thread at runtime? Sorry? I didn't hear you.
It's a program in execution. It will reside in memory.
It will reside in the memory. Okay. So here is your program. Okay. So which program? So I created all this window class and thread class and so on, right? Right. So, okay. So Java will create bytecode. Okay, that's what the Java compiler does. When you run the Java compiler, you get bytecode. Okay. So there's a file which contains the bytecode. Okay. So let's say this is the file for, I mean, whatever. Okay. Right. So this creates some some code. So now this is sitting somewhere. Where is now? What happens? Yeah. So let me go back. Okay, so there is also something called test windows. Okay, and the test windows has a main, as you see. There's a main method. So that is also sitting somewhere. Okay. So maybe this is test windows. Let's say this is the object code. Let's assume that. Let's forget the source code. The source code, let's say, is somewhere on disk or somewhere. Okay, so here is test windows. Here is windows. Now what happens? So here is here's test windows. There is a main. So there is some main is, let's say this is the address of main. So here is the code for main, which has been compiled. Now what happens? Right? Yeah. You start, I mean, what will the, at object time, what will happen? This address will be loaded in the program counter, and so execution will begin of this code, right? So, okay, to begin the execution of this code, the first thing you hit is this, okay? So what will this do?
The process will create 5 objects of that type in the memory.
Okay, 5 objects. What is an object? Right. Okay. Okay. Here is 5 things. Let me call it. Okay. So this is this. What is it? W, right?
Pointers in an array.
Okay. So this is W now.
And then 1 for thread. It's thread. T.
No, okay. 1 for thread T. So some space is allocated for these things. That's okay. So this is a declaration. So this will just allocate space. Now you come here. You start executing. There's some integer variable I. Here is I. Okay, that is initialized to 0. It's set. Then what is W0 is created at this point. Okay, and T0 is created. What happens at this point? Huh? Sorry, first was?
Windows 5 and thread 5.
Yeah.
We create just some sort of space for reference.
Correct. Yeah, yeah.
And in this case, new Windows and new thread,
Yes.
it will create the actual object.
How? But what is the actual object? This is the question which I'm asking, right? So I'm just trying to see what I mean, let me explain what I'm trying to do. I'm trying to see exactly what happens when you just write some simple code like this. In Java, of course, everything runs well, but we are trying to understand what actually is happening inside the machine at this point, right? This is what we are trying to figure out. Okay. So one array is created. So of course, there's this space for pointers and so on. So let's now say W0 is new window with the parameter 0, right? So what will happen at this point?
An object of class Windows is
Okay. So here's the class window. Let's say this is what it looks like. Okay. Now what is an object of class Windows? And is it a copy of this? So let's say here. So I've created a copy of this. Now,
I don't think that's a copy. That part was the code. And this will be the data that is required to maintain that.
correct. So this will contain. Okay. So the class of Windows, it has got methods and it has got data variables. Okay. So basically all the method code is here. Okay, there is no space allocated for the data variables. So when you create an object, this W0 object, then all the data variables, there is space for them created at this point. Okay, fine. So, okay, so this is W0. Okay, and now how this is given a parameter I. So what is I? Yeah, in Windows there was a field called ID, right? Which is actually what is printed out on the screen. Yeah. So that field ID. So this is actually in the ID variable of the class of the object w0. Okay, so this is w0.id, and w0.id is set to I, which is passed. So this will be basically set to 0. There will be an instruction which will do this. Okay. Now you create this t0. Okay. How does this? What will this t0 do?
It is giving the class object of class where the run method is available.
Run method is somewhere here, right? There is a run method here. Okay.
It is feeding the object of that class where the run method is located.
What do you mean feeding? What do you mean feeding? It's not a cow or something, right? So, yeah. Okay. Yeah. Okay. So. Yeah. So T0. Okay. See, Java doesn't do different things for different classes. Whatever it did for a class called window, it will do the same thing for a class called thread. What it do for a class called window? It created space for the data variables. What will it do for the class called thread? It will create a space for the data variables, right? So whatever we don't know the definition of thread. It's somewhere inside. It's a built-in thing inside Java. So whatever was there, I mean, whatever variables thread things are supposed to have, it will have all those things. Right? That's what it will create. Okay, but now here this is passed a parameter wi, meaning w0 at this point. So what is this w0?
Maybe it creates a pointer to the window object.
Yeah, so inside the T0 class there will be a pointer to which object is supposed to be instantiating this class. Okay, so maybe there's a pointer set like that. Okay, so that's what will happen. Okay. And now you say ti.start. Where is the start? Huh? Yeah, but what is start? Yeah, but where is the method? So this method was created when you did this declaration. At that time, just as we did something for window out here, okay, there was something created for thread also. And this is the code for all the methods of thread, and maybe this one is called start, right? Okay, and so at this point you want to call t0.start. What does that mean? You want to save the present program counter on the stack and go to start executing t0.start. Okay, how does this happen? Your present program counter is somewhere here, right? Because you are running this test windows method. Okay, so maybe you have gone down a few lines. You come somewhere here. Now, how do you go to t0.start? Yeah. So in addition to this, I mean, different Java implementations can do these things differently, but at an abstract level, apart from all these variables, these things also have addresses of all the methods, where the methods are. So there will be a run method here that will be set to point here, okay, and there will be a start method here, okay, and this will be set to point to this place, right? So when you say something like t0.start here, this thing goes to t0, finds out the address of the start method and calls this start method, right? This is what happens. Okay, let's expand this machine a little. We need more memory, right? So okay, so now this method it executes, and at the end this is supposed to return. Okay, normally a method will return to the caller, okay, but the start method is a special method which after this will just go straight back to main, okay, or maybe even straight back to the operating system. Okay, so this is what is going to happen at this point. Okay, fine. So you go through this, So this has started. Now you increment I. Now you create W1. Okay. What is W1? Okay. So W1 is, you do exactly the same thing that you did earlier. Okay. So here is W1. Okay. And there is some run method inside this, and this run method is set to point here. Okay. Then there is a T1, and there is a start inside this, and this start is set to point here. Okay. And then you do T1 dot start. Okay. So what happens at this point? Okay. Right. So here is W1. So what is the address of W1? Here is W1. What is the address of W1? It will find out this W1 dot run, load that thing, and start executing this. Right. That's what will happen. But you have to do something more. Okay. What prevents the execution of W0 and W1 from getting mixed up? Okay. Because these are concurrent threads, they are supposed to run by themselves. Okay. So supposing this thing is running, I mean our start method is very simple. Our run method is very simple. All it does is it just prints something. But in principle, it could be, computing factorial recursively or something. Right? It could be doing some complicated thing. It could, right? So it could be still going on while, so W0 dot run could be running, okay, and doing some long computation. Now you start off W1, okay, and now let's say that thing has made a recursive call, and this is, let's say W1 at this point when it is running. So here is W1 inside the run. Let us say it's computing factorial 5 at this point of time. Okay. It's a recursive factorial program. It's computing factorial 5. Now this guy starts off and it starts with computing factorial, and let's say it's computing factorial 26 or something. Okay. So now these two things will get mixed up, right? How will you avoid that? Yeah, so this is the key thing. Okay. So a thread has its own stack and runtime context. Each thread. So since when you create this T0, it has not only all this data, but it has a stack also. Okay. Similarly, when you create T1, then T1 will have its own stack also. Okay. So the computation of factorial here, 26 will be on this stack, the computation of factorial 5 will be on this stack. Okay. Fine. So then the two processes can go ahead and do their work. Okay. This is clear? This is the main reason why you want to call the thread class. And why don't you just make it a method like any other method? Because that method will not create its own stack. What the thread class does is it creates its own stack. Okay, because it knows that this is going to implement a concurrent process. Right? Is this clear? What is happening? Okay. So in particular, the reason why you have to do all this, if you want to create a thread within a thread, you have to do it using runnable and not using thread, is because that runnable class has to have the potential for creating more threads inside it, which means it should have the capability to generate even more stacks inside it, right? So all this has to be taken care of. So the operating system, or rather Java, actually gives you two different mechanisms to do this, so that the operating system can handle all this properly.
So as far as memory is concerned, we want to have independent stack and everything. We are having the process. Immediately after the creation of the object itself, we need the attention of the processor. But
Yeah.
we do not have memory processing elements are available. So
Yeah.
how that mapping will be done in the...
Very good. So the question is, what are we doing with these things? here are all these, that is our multi-core thing, right? So there are all these processors, okay? So how are they coming into the picture? Because otherwise, why are we using this at all? We could have done this on a single user machine, right? So who does that mapping? Who's the process manager? I see. Okay. No, that happens. So that happens inside an operating system. Okay. But here we are writing this inside the programming language. Okay. So yeah. So what the programming language does is basically it says, okay, I created these pieces of code. Okay, I created this process of code, and I brought all this I created space. Now at runtime I'll create variables for this, and here when I make a call to T0 to create this thing and start off, the question is, where is this code for this T0 and the stack and all this, where is it going to be, right? Okay, so these things make sense. In order for these things to make sense, what we have to realize is that actually the memory is not like this. Memory is partitioned. Okay, in a multi-core processor, what happens is memory. I mean, it could even be physically separate, but I'm not assuming that right now. It could be but memory is divided into different portions, and what we have is what the operating system does is it says, okay, this guy is at present using this guy is going to use this guy is going to use this part of memory. Okay, and so when you create W0, this will be, let's say, on processor 7, okay, and so processor 3, let's say, and processor 3 is going to run this. When you create W1, maybe it's created on processor 2, okay, and then processor 2, so it will be in this part of memory. Okay, so you don't have one big memory. The memory is divided up, and as I said, I mean, you can call it process manager or whatever you like, but at runtime it is decided because it has to be at runtime, because we don't know when that process will when your program is going to create that thread. Right, that is not known to the. It can create, as I said, there could be. I called start immediately, but I could have called start after doing some long computation. Right, so it's only at runtime that the operating system knows that now I have to create a thread. Okay, so when a thread has to be created, then you look at what all processors are available. How many threads is this guy handling? How many threads is this guy handling? How many threads is this guy handling? And you put the new thread that you created, you put it on the queue of that processor. You create space for it inside that processor. Okay, and then you start. Then when it is scheduled, at that point that thread starts running. Yeah.
Actually, in practice, one thread or one process will not even fix this one particular process.
Load balance. The operating system will try to do load balancing dynamically.
Yeah.
So, I mean, even without multiprocessors, we had threads, and all it has to manage is which particular context the processor is in, and rest of the contexts are frozen.
Yeah.
And when it's time to switch, then this context is saved and that context
Correct.
is loaded.
Correct.
And in fact, the number of threads and number of processors need not have any relation at all.
Yeah. And as is usually the case, because when you say multi-core doesn't mean you have an unbounded number of processors. Multi-core means you have 4 cores, 8 cores, I don't know, 64 cores, some such number you have, right? Whereas in the program you can create an array of 100 threads, 1000 threads. How does it matter? Programming language doesn't stop you from creating threads, right? So there has to be some mapping done, and this mapping is done at runtime, right? So this is the kind of setting you have to do. So what I want to say here is that although this looks extremely simple, and you just write some 10 lines of Java code, but but actually lots of things are happening in the background. Okay, and inside this, what you have is you have to also imagine the following situation. I mean, as Abhay and Suresh were saying, you don't actually know which processor and which core this is going to go in. So when you write this code, you have to write it in a very careful manner. It has to be reentrant. That's the technical word. Okay, so that it does not matter actually whether that code, which core it is, and where it will just run completely indirectly through pointers, finding out where. See, it might be that this W0's data variables are here, but this thing is sitting somewhere else. But this W0 could have been here, could have been here, could have been here. That is not known. So the code has to be written in such a way that it doesn't matter in which partition it is, it has to run correctly. Okay. So this is something which is makes the compiling, but all this is done at the time of compiling and loading, right? At runtime, everything is set up so in such a way that you can keep switching context without any problem. Okay, so this is concurrency, and concurrency is by far the easiest thing in this whole business. Okay, and so let's come now to the more difficult things. Okay. So here I'm just giving some example of how to do parallel programming. So if you have done this before, then this is very easy to see, but if you haven't, then it's just the kind of issues you have to think about when okay. So let me take, maybe I have an example somewhere. Okay, let me do this. Okay. I don't have that example. Okay. So here I am just pointing out this. So just look at this code. What we are doing is, in a loop, we are creating a thread. Okay. So this thing is a thread. So we this thing extends thread. So we create it and we start it off. Okay. This is the loop that we created. Okay. So okay. So what we have is that every iteration spawns 5 threads. Okay. But even though threads are supposed to be lightweight, you have to allocate the stack space and so on. So they are actually costly in terms of compared to usual memory operations. So if you want to program things better, then you should do something like this. Okay. Okay. So here is so I've created these 5 threads. Okay. Once and for all. I don't do it, and here what I do is I do one iteration of the ith job and then I synchronize. Okay. So if this is not clear, let me just explain. What I was doing in the earlier thing example is I was doing one iteration. Okay. Then I was doing some next iteration. Then I was doing next iteration. Right. So I was creating 5 threads, doing one iteration. 5 threads are over. Then I create 5 threads, do one iteration. Okay. Instead, what is done in this code is I create 5 threads. And here at this point, I don't kill these threads. I synchronize. Okay. So I create a barrier here. And I synchronize. Then I do this the next iteration. Then I create a barrier here and I synchronize. Okay. Then I create a barrier here and I synchronize. Okay. So this is what is said here. So you do one iteration, you synchronize. Then you do the next iteration, then you synchronize. Then you do the next iteration, then you synchronize. Okay. So that way you don't keep on creating and destroying threads. Okay. Because for every creation and destruction of thread, you have to go to the operating system. Okay, and then the operating system has to allocate the stack and execution context it has to create, all that it has to do. So you don't go, you try not to do that. Okay, you do the synchronization within your programming language. Okay, so how do you do the synchronization? Yeah, I'm just coming. So here it. Okay. Okay. So yeah. So here is a barrier. Okay. So barrier can be, for instance, an integer. Okay. And what a process does is any process which comes here, it reaches that point, it increments that counter. Okay. Let's say initially the counter is set to 0. When the counter reaches 5, then you know that all 5 processes have completed that iteration. Now you can continue. Okay. So this is a busy wait. So count is incremented. So and then you wait until that count becomes 5 or whatever. When the count becomes 5, okay, then of course you have to reset the count again to 0 because there may be another barrier later. Okay, this barrier can be inside a loop like we have here. Okay, so how do we do that? Okay, so instead of having a count, we have done it now using a Boolean array. Okay, arrive, and instead of doing count, incrementing count by 1, I just set the arrive variable saying I have arrived at the synchronization. Okay, and now what you are waiting for is arrive 1 plus arrive 2 plus arrive 5 should be equal to 5. This is what you are waiting for. When that happens, you can continue. Okay, but unfortunately, this is also inefficient. Why is this inefficient?
That happens you have to set your own arrive to 0.
Yeah, sure. Yeah, but I'm saying in order to do this, the problem is that there are a lot of processors trying to access one shared thing in between. Okay, so that, and you have to keep checking this. This is actually implemented like a busy loop. At least that's what we saw above. So you're actually keeping on checking this all the time. Okay, so this is an inefficient thing, and everybody is trying to access that arrive array. Okay, so this is something which is inefficient. Okay, so then there are different ways of doing this. Okay, so here is a centralized method. So in a centralized method, what you do is you have two booleans, arrive I and continue I. Okay, and you first set arrive and then you wait for the continue to come from somewhere, and the process and then there is a coordinator, and what this coordinator does is it waits for all the arrives to become true, and then it sets all the continues to true and then continues, right? So the continue process is each continue process is looking only at its own continue variable, okay, and it continues with that. Is this clear what is happening? So there's this centralized, this is done with one coordinator. Okay, you can have distributed barrier synchronization. Okay, right? In this case, instead of having one centralized coordinator, you have a tree of processes of coordinator. Each process, you arrange the process in the form of tree, and each process acts as a coordinator for its children and passes the result back up. So you can create so there's you wait for arrive from left, set arrive left to 0, or you wait from arrive from right, set arrive right to 0. You set your own arrive, then wait for continue from the parent, then set the continue of the left child, set the continue of the right child, and so on. Okay. So here is what I wanted to say. Okay. So the real difficulty of programming, concurrent programming, is not so much concurrency, because concurrency is actually taken care of by, in some sense, the programming language and the operating system. You don't have to worry about it too much. Okay, but what the processes have to do is they have to coordinate with each other. Okay, and this is very hard because you just write some simple line of code and it will be inefficient. Okay, so you have to think about how to do it, and you have to program it, and you have to come up with some strategy like this. Distributed barrier synchronization or something like that, right? So that is the hard part. So the real difficulty in concurrent programming is communication, okay? Because at some point you have to communicate between threads. That is expensive. How do you keep it down to something small. You don't want to do too much of it if you can help it. This is the essential idea here. Yeah.
What is the difference between software thread and hardware? Like hyper-threading and all this?
I have no idea. Okay. So I now want to jump straight away to let's see, communication. So let's see, how would I go there? So this is all Suresh's lecture. Are you doing all this? Anderson Locke. Then Craig Landon, Hagerstead Locke. This is some Mellor, Crummy and Scott Locke. So, okay. So I want to come back to this. Okay. So I want to talk about now communication, which is message passing. And there are two kinds of message passing, asynchronous and synchronous. Okay. So asynchronous message passing is basically email. Okay. So in which when you send an email is different from when the email is received. That is the key thing. So there are two separate events, and if you want to receive a message, you have to wait until the message comes. Okay. But if you have to send a message, you can send it. And, okay. Some email program will take care of it. And synchronous message passing is like a phone, okay, or accessing a web page. Okay, there is no separate sending and receiving. Okay, right. So you, even if you want to, all you want to do is, all I want to do is to tell Ramchandra something on the phone. He still has to be there on the phone to listen to me. Otherwise, my phone call doesn't work. Right. So that's synchronous message passing. Okay. So. Yeah, so of course programmers like asynchronous message passing, right? But then somebody else has to implement the email program, and you send your email, that's very good for you, but then somebody has to write an email program, right? So that's, so here is, okay, I don't think I want to go into this example. So this is a dining philosopher's example, which is a famous problem in distributed computing due to Dijkstra, and I programmed it using this. Okay, so I want to now talk about this particular thing, which is how will you actually do this asynchronous message passing and synchronous message passing, let's say in Java. So this is according to, so this is code which I have taken from a textbook and which I will point out is wrong. Okay, this is not the same textbook which I mentioned. This is not Greg Andrews' textbook. That's very good. So what they say is that asynchronous message passing is done by extending the class selectable, and so there is a send method, there is a receive method, and then so it looks. Okay, what threads do is they use this method. So there's a, let's say, some producer consumer kind of example. So producer implements runnable, okay, and then it has a run method, and somewhere it does send. Okay, you call that send method. Okay, I don't want you to kind of understand every bit of this. I just want you to look at some basic things which are happening, and then I'll point out what the mistake is. So here is a consumer process. So this is a consumer process which implements runnable, okay, and it has some code, and finally what you do is you do a receive call, and then you get actually that variable, right? So this is the asynchronous message passing. So now we come to synchronous message passing between threads. Okay, so what is synchronous message passing between threads? There is a class called channel. Okay, so remember the other one was called port. This one is called channel. Okay, so it has some methods, and here is a sender process. Sender implements runnable. Okay, and then there's some run method, and this calls the send method of this channel. Okay. Okay, and here is the receiver class. Okay, and this implements runnable, and it calls some receive method of this process. Okay, and this is the mistake. Okay, which is that if you see this, what happened in these two things, there is actually no difference between asynchronous message passing and synchronous message passing. Right? Okay, the names might be different, but you did exactly the same thing. You created one thing which extends selectable, and you had a send method, and there was a receive method, and you did exactly the same thing. Right? So, why has this book, this is a mistake, why has this book made this mistake? Okay. That's because what it calls message passing, and which might make sense for a multi-core sort of setting, is message passing between threads. Okay, and you assume that threads are actually implemented the way I showed you there. So they are all essentially in the same area, right? So it doesn't matter whether you're doing asynchronous, synchronous, it's all the same communication. Okay. Right? Whereas when you send email, okay, the email does not go, me and the receiver of the email are not sitting on the same machine. Okay, it's not that we are both sharing one multi-core processor. Right? The person who receives the email is sitting somewhere else and has his or her own machine. Right? So you cannot use this kind of things to actually implement an email program. Yeah.
I think the difference is whether the call gets blocked or not blocked.
Yes.
Asynchronous doesn't get blocked.
Yes.
The call immediately returns.
Yes.
And the message is buffered.
Yes.
Whereas in synchronous, the call gets blocked. So that's the basic difference.
That's true. I mean, that's what I said. It's like email versus phone,
Yeah,
right?
So here the difference is there. So in one implementation, the call doesn't get blocked. It immediately returns in asynchronous.
Okay.
Whereas here, in this case, the channel.receive will get blocked.
I agree. Okay, but I'm saying that I'm pointing to another difference. Okay, the difference is that when you do message passing, okay, when you're sending messages, you don't implement it on. You do message passing. When you use email, you don't use email on the same machine. You're doing email on some other machine. So, for instance, supposing you are accessing a web page, right? If you're accessing a web page, then that web page is not sitting on your machine. Okay, you have to actually access that machine. So, how do you do that? Okay, so I'll just show you the kind of flash the code at you just to, okay, how do you just to show you that there is a difference. Okay, so first, basically, okay, you have to call some package which supports some communication. Okay, so in particular here I am using TCP/IP. Okay, right. So what do you do? So here is some synchronous class. So I do it using sockets. So I create a server socket, a socket class. I create a reader stream. I create a writer stream. Okay, and then I try to open that stream. Okay, if there's if that does not happen, I open. I give some error message. Otherwise, okay. Otherwise, I have actually succeeded in creating this. I create now a file reader class. I get line by line everything, and I print whatever I do with this, right? So this is what I'm saying is I had to create a reader object, a buffered reader object, and similarly on the other side a receiver object. Okay, and here is the program on the client side. Okay, so I created socket on some domain, okay, with some port address, then buffered reader class I created, print writer class I created. Okay, okay, and what you will do is each program is compiled on its host machine. So on the server thing I compile this and create this, then on the client side I compile this and run this separate. So these are running on two different machines. Okay, and now you can ask questions like this. Okay, what happens if the client is started before the server? What happens if two clients try to connect to the server at the same time, and so on and so forth. You can, these questions now make sense. Okay, whereas in that setting that I talked about, actually nothing of this kind can ever happen. Okay, so this is the summary of the asynchronous message passing. Okay, which is you create a new server socket on a port, wait for the socket with the client connects, create input and output streams, and use the streams like you use streams in Java for instance for reading and writing. And and you have open a socket connection to a port, create input and output streams for using socket, and use them like any other stream. Okay, and here is how you do synchronous message passing. This I am doing using a class called RMI. Okay, and again there is a RMI class. Okay, so I am programming the same application. Okay, so you have to create. Okay, so first thing you have to create a registry service. Each server object has to be registered with those things. Okay, and you should be running the registry as a background job on. Okay, okay, so you will create some thing like this where you start the server off. Okay, and then you have an RMI compiler which creates proxies and skeletons, and then the JVM will run a synchronization protocol between the proxy and. What does the client program need to do? The client program has to create a security manager. Okay, and then you set up a security manager, try to connect to that process, handle errors. So here is the summary. Okay, you create an interface class which extends the remote method. Okay, then you have a server class which extends this unicast remote object. Okay, you compile with Javac, and then you run this RMI compiler to create stubs. On the server side, you run a registry as a background job, and then you compile this. Okay, on the client side, you set up a security manager. You run the client using something like this, and client looks up the server and then makes a connection. Okay, and now the server's remote methods can be implemented just like a usual Java call. So all I'm saying is that finally it comes down to whether you are making a call to just like calling some other method, you are calling a remote method now. Okay, but in order to set up that remote method, there is a lot of background job work you have to do, and all that background work you had to do because you are connecting to some other machine somewhere else. Okay, and this is the difference between message passing just between machines, not just between threads. If you are just communicating between two threads on the same thing, then there is no problem. You never have to go to any other machine, so you don't have to do all this. But if you actually want to communicate between machines, I mean, if you actually want to program something like email or program something like that, you have to do all this work. There is no escape from this. So, okay, so I can actually, I'm going to just stop with this. So what I wanted to say is when you are actually, I mean the way this book was written, okay, probably the book is used in some setting where there are students using threads, creating threads and using them. So it works correctly as far as that particular setting is concerned. Okay, but if you actually want to program applications like email, or which is what, I mean, after all, how do you differentiate asynchronous message passing from synchronous message passing? The fact that you try to communicate with somebody and that person is not there, then what happens? This is really the key thing. Okay, and this makes sense when the two things are physically separated from each. It's a matter of just routinely going through all these steps. But it's not as simple as just doing one call and thinking that everything is over. It's not as simple as threads. Okay? So what I wanted to point out to you is that in some sense, in the earlier thing, the thread example I showed you, that while programming threads, you have to actually program communication very carefully, right? And here, when you have to actually do something between machines, and again, programming communication is taking a lot of effort. Okay? And this is natural. I mean, we all know that it's, even forget computers. I mean, among human beings, if you want to actually, if I have to sit here and give a lecture, and you have to sit and give a lecture in your college, okay, there's no problem. It goes on, okay. But supposing we both are jointly trying to give a lecture, and we want to do something, then it's complicated. You have to set up actually some kind of video conferencing or something you have to do. So you have to do some work, some background work. Only then things will work, right? And that is what I'm trying to illustrate. That the point is, in concurrency, the main reason why concurrency is difficult is because you have to do communication between concurrent process, and it's that communication which is difficult. Okay, so I'll stop with that. Thank you. Questions? Yeah. Yeah, but
actually you differentiate concurrency and parallelism?
See, the way I did this in Java, okay, that in Java there's nothing particularly to say that you are on this machine or that machine. So the way it's actually differentiated is by what all you do in order to start that concurrent execution happening. Right? So when you actually start using some specific packages, right, which will actually communicate with another machine or something, that is what creates this thing. Again, in Java, if you look at between a thread and any other object, it doesn't look like there is much difference. You just create one thing extending thread. Okay? But it is in the implementation that all these things matter. In the implementation of the thread class, one stack will have to be created and something. Right? So the way programming languages are designed to make things easy for you. So they just say, okay, our mechanism is procedure call or something. So everything looks like procedure call. Okay. But behind that procedure call, what all is going on, that you have to understand, and that is where all the difficulty lies. Okay. So that's what I was trying to illustrate out here. Yeah.
It could also be terminology. Traditionally, parallel algorithms as such people have used the terminology to talk about where various things happen in parallel, but there is one centralized control that drives all these different one centralized results. For instance, in parallel architectures like the supercomputers and so on. And as opposed to distributed algorithms where there is no centralized control. Now, concurrent, in fact, Dijkstra suggested as an abstraction for thinking of any of these things. So you just think of concurrent processes, whether they have centralized control or distributed control, or whether they operate on synchronous mode or different time scales or whatever. So concurrency is a kind of an abstraction of things happening in parallel in whichever kind of coordination. But this is all just terminology, finally what we choose to call.
I would also think that it's a difference in emphasis. For instance, in the barrier example that he gave, so the actual code for the barrier synchronization would be something that involves, somebody who studies concurrency would study. Whereas how do you split the task into various elements so that at each round they collect the data and go forward, that is a parallel algorithm. The mechanics is something that somebody who knows concurrency.
But the same procedure is followed. Actually, I have gone through Michael J. Quinn parallel algorithms.
Yeah.
Same things are discussed for prefix summation or whatever it is. you create processes,
Sure.
different
No,
tasks,
but then they wouldn't process
bring the data together.
Yeah. No. But I'm saying when you read an algorithm, you don't actually see what happens at the level of running the program.
But there is no barrier there. But
Sure, I agree. But what I'm saying is only when you actually see how is this being implemented on a multi-core processor that all these issues now start coming out, right? You can just analyze it in the abstract, right? That's also possible, right? So you just analyze this and you say, okay, I'm doing this computation parallel with this. So actually, although it looks like it could be taking quadratic time, actually it's happening in linear time, in parallel linear time, right? You could do some analysis like that. But how did this parallel linear time actually happen? How does it actually happen on the machine? Right? So this is what I'm trying to illustrate here, that when you actually run these things, you have to set up some mechanisms with using programming languages. And if you want to, illustrate this to students and give them an understanding of how actually these things work, then when you try to run these things, you actually figure out this thing. I mean, fortunately, this is there in a textbook. Okay, so I didn't. It's not that I had to do actually all these experiments and figure this out. I got this from a textbook. But what I was pointing out is that sometimes textbooks also have mistakes. Okay, and in that particular textbook, I was very puzzled. I said, how can asynchronous message passing and synchronous message passing be the same? They can't look the same. It's not possible. And then that's how. Then I went into the thing and then realized that this is actually wrong. Okay, and not wrong, but it is designed to work in a very simplified context. Okay, which will not work all the time. So if you actually have to program between machines, communicate between machines, that what he said is just will not work. You need to do something more. Right? So that's what I was trying to illustrate. So there is, but I must say that these. So for instance, if you look at, say, your mobile phone, right? So you want to call Ramchandra here or you want to call somebody in the US, the only thing that matters is what prefix you put, right? So you just, there's some digits and something happens. But how does the call to him go and how does the call to the US go? Right? So is it the same mechanism which is followed? So when you look at actually the implementation, then you figure out actually how these things are being done. And in general, what people are trying to do, at least what the mobile phone industry is trying to do, is to make everything work in a uniform way so that things work the same. Right? But there are differences, and that is why the cost to him will be cheaper. So that is built into that factor out there. Right? So whereas a call to the US is going to be more expensive because you have to communicate with some other company at some point of time. So that you have to do. So everything looks on the face, it looks very similar, but when when you look through the implementation, then you find actually what all details are going. That's why I did this whole business to show you, to try to figure out where exactly different things are sitting.